In this video, we're going to talk about how to graph many different functions using transformations of graphs. In order to use these transformations that we're going to learn about, you will be expected to know the basic graphs of some fairly standard functions. You probably already know a lot of these graphs now. If you don't, you need to make sure you write these down. We have 9 basic graphs that you should be very familiar with, because it makes your life a lot easier when graphing more complicated functions. So the first graph of a basic function that you should know is a linear function, which we've been talking about a lot in the previous videos. So we have linear functions and we have constant functions. And we kind of group those together in our first type of graph. So your linear functions are the ones that make straight lines when you graph them. And they look like f of x equals mx plus b. And so the graph of a linear function is always going to be a straight diagonal line. They can be going up to the right like this, or they can be going down to the left, but the whole point is it makes a nice straight line. Constant functions are very similar, but if you remember from one of the previous videos, constant functions are ones that just look like f of x equals a constant b. So those are also linear, but they make a horizontal line. And again, this horizontal line can be at any place on this grid. It all depends on what b is. The important part is that you know that a constant function is a horizontal line. All right, our next basic type of graph that you should be very familiar with is the identity function. And the identity function is also actually a linear function. It's just a very particular one. So we give it its own special spot at number 2. The identity function is the function that takes in the input of x, and the output is also x. It doesn't do anything to the input. If you graph f of x equals x, you get a nice straight line, and it's a perfectly diagonal line, 45-degree angle going through the origin. Number 3 is your quadratic functions. In particular, the quadratic function f of x equals x squared. So this makes the graph of a parabola, as I'm sure you already know. I'm going to make sure I put my points in the right place to be very precise. It has points at 0, 0, 1, 1, 2, 4, negative 1, 1, and negative 2, 4. And that's usually enough for me to get close to the right shape. Wow, that was terrible. All right, let me fix that a little bit. There, we have a parabola. Of course, it's going to be more perfectly shaped when you have graph paper and you're not on a whiteboard, but this should be a U-shaped graph. It looks like a nice parabola. You can also use your graphing calculator to see exactly what it looks like, but you get the general idea. Our fourth type to learn about is the cube function. Which is f of x equals x to the 3rd power, or x cubed. The graph of this function, it goes through 0, 0. We have a point at 1, 1, and a point at negative 1, negative 1. If I went over to 2, the next value for my y would be up at 8. The cube function has a shape like that. Number 5 is our square root function. F of x equals the square root of x. So the square root function, we have a point at 0, 0, 1, 1, 4, 2, and it keeps going on forever. It's still going up as it goes to the right as well, it just doesn't go up very quickly. That's what our square root function looks like. Number 6 is the cube root function, which looks kind of like the square root function. Except it continues on both sides because we're allowed to take cube roots of negative numbers. I guess I don't need all of that. So your cube root function has points at 0, 0, 1, 1, negative 1, negative 1. It kind of looks like the cube function, except it's been flipped over. So it's a lot flatter than what the cube function is, but still makes kind of a weird S-type shape. It's just flopped over on its side a bit. So that one again is f of x equals the cube root of x. Number 7 is the absolute value function. So this one is f of x equals absolute value of x. That one makes a nice V shape. We're going to have 0, 0, 1, 1, 2, 2, 3, 3 going in this way, and negative 1, 1, negative 2, 2, negative 3, 3, diagonal line going the other way, and you get a nice V shape. And then I just have one more. I know I said 9 at the beginning, but we have that constant function lumped into number 1. So we do have 9, just I labeled them a little bit different. We have 2 for number 1, and everything else gets its own number. The numbers don't even matter. It's just trying to keep your notes organized. So number 8 is the reciprocal function. This one is f of x equals 1 over x. And the graph of this function is a little strange looking. We have a point at 1, 1, and negative 1, negative 1. But we have a lot of asymptotes going on. And you get this graph of the reciprocal function. So all these functions that I just quickly graphed for you, those are graphs that are very, very standard and we expect you to know. When we're going to learn about all these translations of graphs, we need to first figure out which one of these basic functions is most similar to the thing we're trying to graph, and then we will learn how to shift it and stretch it and shrink it and flip it around to get the graph of the function we're trying to actually graph. So the first thing we need to learn about is vertical translations of our graphs. So let's define our vertical translations and do a couple examples. So consider a function, f of x, let me actually say y equals f of x. And let's let k be a positive real number. Then two things are true. The graph of a different function, f of x plus k, is the graph of f of x shifted k units up. And the graph y equals f of x minus k is the graph of f of x shifted k units down. So if you have a function that looks like one of our basic functions, but there's a number added or subtracted to it, all you have to do is take the graph of the basic function and shift the whole thing up or down. So let's do an example using these vertical translations. Let's graph g of x equals the square root of x minus 2. So notice in this function that we're trying to graph, one of our basic functions is there. It's the square root of x. So we're going to take the graph of square root of x and shift it vertically based on what this negative 2 is telling us to do. So what does the negative 2 tell us? It tells us we're going to be shifting down 2 units. So the first thing I'm going to do is take a look at the graph of square root of x. I'm going to do it as a little dashed line because we're not actually trying to graph that one. There's square root of x, and we want to graph square root of x minus 2. So to do that, I'm going to take the points that I know on my graph and shift them all down 2 units. 1, 2. So when I take my point at 0, 0, move it down 2 units, I'm now down here at 0, negative 2. My point at 1, 1 is now at 1, negative 1. And my point that was at 4, 2 is now at 4, 0. And when I connect this, it's going to have the same sort of shape as my square root of x, but going through slightly different points. Let me fix up my axes that I messed up there. And there we go. In red, that is the graph of square root of x minus 2. So that's not so bad. Of course, you can always graph these by just making a table of points like you may be used to. You could make an XY table, plug in various values for x to get the y values, plot the points, and connect that way. But if you already know the graph of these basic functions, it's a lot quicker to use the transformations that we're learning about in this video. So part B of this example, we're going to graph another function. Let's graph h of x, which is the square root of x plus 3. So this is very similar to our part A. On part A, we shifted down 2 units because I had a minus 2. This part B, we have a plus 3. So this means we're going to go up 3 units. So again, we're going to have our basic square root graph. which looks something like this. There's square root x. And then to graph this h of x, I need to move that entire graph up 3 units. So to graph that, let's take the points we know and move them up 3 spots. 0, 0 is now up at 0, 3. 1, 1 is now up at 1, 4. And then this 4, 2 is going to be all the way up at 4, 5. That is right about here. Now, it would help if I had a graphing whiteboard. But now when I connect these dots, we get the square root of x plus 3. It's the same exact shape, it's just shifted up 3 spots. All right, so that's how you deal with your vertical translations. You take the graph of your basic function and just move it up or down the number of spots it says. Not too bad. The next thing we need to learn about is horizontal translations. Very similar to the vertical ones. So for our horizontal translations, consider a function y equals f of x, and let h be a positive real number. Then we're going to have two things that are true, two different types of graphs that we can get using our horizontal translations. The graph of y equals f of x minus h inside the parentheses is the graph of f of x shifted h units to the right. And the graph of y equals f of x plus h in parentheses is the graph of f of x shifted h units left. And now I'm underlining that right and that left because I've learned that sometimes this is counterintuitive to a lot of people, myself included. When I first learned these translations, I always wanted the minus one to go to the left and the plus one to go to the right, but that is not how it works. The vertical translations are much nicer in that regard. They match what your brain is thinking to begin with. But you have to remember with the horizontal translations, when it's inside the parentheses with the x, if it's a negative, it goes to the right, and if it's a positive, it goes to the left. So let's do an example using a horizontal translation. Let's graph g of x equals the absolute value of x plus 2. So first thing you have to do is think about which one of our basic graphs is most similar to this function. And that, of course, is going to be the absolute value of x. That's that V-shaped graph. So then I just have to figure out which way it's going to be shifted. All right, so let's first graph absolute value of x. Remember, that's the one that has the nice V shape, diagonal lines going in both directions. There's my absolute value of x. Now I have that +2. Which direction is that going to shift? Well, that minus tells you it's going to shift to the left. So I'm going to take this entire V shape and shift it all to the left, 2 spots. I'm going to take this point at 0, 0, and it goes to the left 2 spots. This point at 1, 1 goes to the left 2 spots. 2, 2 goes to the left 2 spots, and so on. And I get a nice V shape again. It's just shifted over to the left 2 spots. And there is my graph of absolute value of x plus 2. Now, is it possible to have more than one of these translations in the same graph? Absolutely. In fact, our next example, we're going to have both a vertical and a horizontal translation. We are going to graph q of x equals the square root of x plus 2 minus 5. So I know I'm going to deal with my square root graph. So let me first put my square root on here. There's my square root of x. And now we just have to figure out what kind of translations these are. So this plus 2 inside the parentheses, or not inside the parentheses, underneath that square root, this plus 2 means I'm going to go to the left 2 spots. So if I move everything to the left 2 spots, I have that shape, but now I also have to do this translation going down 5 spots. So I've moved to the left 2, and now I'm going to move down 5. And I still get the same type of shape. It's just the entire graph has been picked up, moved to the left 2 spots, and then moved down 5 spots. So that is all of our translations. But there's other things we can still do with our graphs. We can stretch them and shrink them. We can flip them, all sorts of fun stuff. So our next thing we're going to learn about is all of these stretching and shrinking. And we're going to talk first about vertical stretching and shrinking. So we're going to consider a function, y equals f of x. And we're going to let a be a positive real number. Then, if that a happens to be bigger than 1, then the graph of y equals a times f of x is the graph of f of x stretched vertically by a factor of a. So by stretching vertically, what we mean by that is picture grabbing onto both ends of your graph and literally stretching it upwards. That is what vertical stretches do. Now, that is what happens when your a is bigger than 1, but a can be any positive number, so it could also be a number between 0 and 1. If it's between 0 and 1, that's your shrink. That's where you take your graph and pushing it down. So let me write down what happens for the shrink. If your a is between 0 and 1, then the graph of y equals a f of x is the graph of f of x that just happens to be shrunk vertically by a factor of a. So regardless of whether this is a vertical stretch or a vertical shrink, the important thing is that any point xy on the original graph is going to be transformed to a different point x a times y. So any point xy on the original graph f of x is transformed to the point x a times y. So you can figure out what the graph of your function a times f of x looks like by multiplying the y coordinate by a, regardless of whether it is a stretch or a shrink. Just multiplying that y coordinate by a will take care of the stretching or shrinking for you. Now, those are both vertical stretches and shrinks. Now we need to learn about the same thing, but doing it horizontally. So horizontal stretching and shrinking. It's a similar idea. So we are going to consider a function y equals f of x. And again, we're going to let a be a positive real number. Then two things are true. If a is bigger than 1, then the graph of y equals f of ax is the graph of f of x shrunk horizontally by a factor of 1 over a. So this one might feel a little weird after doing the vertical ones, because this time if our a is bigger than 1, it doesn't stretch, it shrinks. It shrinks in the horizontal direction, which you can think of taking your graph and smushing it in. It's by a factor of 1 over a rather than a, so we're going to be dividing by an a somewhere in this. And very similarly, if our a happens to be between 0 and 1, we're going to get a stretch horizontally. So if a is between 0 and 1, then the graph of y equals f of ax is the graph of f of x stretched horizontally by a factor of 1 over a. So similar to our vertical stretches and shrinks, we can take any point on our original graph, so an xy, and then the graph on this new function, f of ax, is going to be the point x over a, comma, y. regardless of whether it is a stretch or a shrink. So any point xy on the graph of f of x is transformed to the point x over a y on the graph of f of ax. So if you have a number being multiplied on your x there, that's going to be doing your horizontal stretches and shrinks. And an easy way to figure out what these points are doing is take your x-coordinate and divide them by a. So let's do an example where we're doing both a vertical stretch and a shrink, and then we'll do a horizontal stretch and shrink. So we're going to graph both y equals 2x squared and y equals 1/2 x squared. The first thing you should be wondering is, what is the basic graph that I'm transforming here? Well, they both have an x squared in them, so you know that your basic graph is going to be our quadratic, just the x squared graph. We know that that looks like a parabola. So let me just get our basic parabola up here. This is just x squared. And so we're going to graph both 2 times x squared and 1/2 times x squared. Now remember, when it's being multiplied on the outside like that, this is going to be a vertical stretch or a shrink. And that means that we can figure this out by multiplying all of the y coordinates by our value of a. So I'm going to graph this one first, the y equals 2x squared. This is going to be a stretch, and we're going to have to multiply our y coordinate by 2. Well, here's my first point at 0, 0. When I multiply that y coordinate by 2, it's still at 0, 0. This one, the y coordinate was 1. When I multiply it by 2, it's now 2. Similar for the negative one. When I plugged in negative 1 for x, I got a y coordinate of positive 1. When I multiply it by 2, we're up at 2. Y coordinate of this point was 4. I'm going to multiply it by 2, which is going to put it up at 8, which is somewhere way up here. And same over here. This had a y coordinate of 4. When I multiply it by 2, it's all the way up at 8. And I end up with another parabola type shape. It just happens to be skinnier. So this guy is 2x squared. So what you can think of is, picture grabbing onto the ends of your parabola and you're stretching it upwards. When you stretch it upwards, it makes the graph skinnier. So my 2x squared made the graph skinnier. Now this 1/2 x squared, this one's going to be a shrink because my a value is 1/2, between 0 and 1. And we have to multiply all of the y values by 1/2. And those are the y values of our original x squared graph. So at 0, 0, we're still at 0. The y coordinate for these 2 points is 1. So multiplying it by 1/2, it's now going to be at 1/2. And then the y coordinate of my points here, 2, 4, and negative 2, 4, that y coordinate's up at 4. When I multiply it by 1/2, it brings it down to 2. When I connect these dots, we still get a parabola type shape. It just happens to be a little bit smushed. There's my 1/2 x squared. Picture grabbing the ends of your original parabola and shrinking it down vertically. So you're grabbing it and pushing it down. That gives us this red shape. And we got that by multiplying all the y coordinates by 1/2. So rather than being stretched up skinnier, it got smushed down and got a little bit wider. All right. Now let's do one of our horizontal stretches or shrinks. This one's going to be a little bit different. We're not going to actually use one of our common graphs. We're going to use a graph that's given to us instead. So let's graph f of 2x and f of 1/2 x using the given graph of f of x. So let's get this graph on here. All right, so my original graph f of x is going to have a point here at 0, 1, a point at -2, -3, and a point at -4, +3. So that's up here. And other than those 3 points, we just have all these other points that come when we connect these with straight lines. So in black here, this is the given graph of f of x, and I have to take that graph and stretch or shrink it horizontally to get f of 2x and f of 1/2 x. So remember, when we were talking before about the horizontal stretches and shrinks, we said that all we have to do is divide the x coordinate by a. So for f of 2x, we divide the x coordinate by 2. For f of 1/2 x, we're going to divide the x coordinate by 1/2. So let me make a quick little table of points just to help us out a little bit. Here's f of x. We also need f of 2x and f of 1/2 x. So I'm going to have 3 different things in my table of points. And I have the 3 points that I can see on my graph. I have the point 0, 1, I have the point -2, -3, and I have the point -4, +3. So I'm going to work first with f of 2x. We're going to do that one in red. So remember, we have to take our x coordinate and divide it by a. In this case, my a just happens to be 2. So you're going to take your point from f of x and divide the x coordinate by 2. The y coordinate is not going to change. So 0 divided by 2 is 0. So I'm still going to have a point here at 0, 1. My -2 divided by 2 is -1. So I'm going to have a point at -1, -3. This x coordinate of -4, when I divide it by 2, I get -2. So I get a point at -2, +3. And then I connect the dots. And you can see we still get those 2 lines connecting all the points. It's just that now I have in red f of 2x. We took the graph and we shrunk it horizontally. So picture grabbing the ends and pushing it closer together. That is what happened here when we divided all of our x coordinates by 2. We're going to do something very similar for the f of 1/2 x, which I'm going to graph in green. Remember, we have to divide the x coordinate by a. It's just this time, my a happens to be 1/2. We know that dividing by 1/2 is the same as multiplying by 2. So remember, we are comparing to our original graph, f of x, which I have graphed in black. None of my y coordinates are going to change, only the x. So 0 divided by 1/2 is 0 times 2, which is 0. So I still have my point at 0, 1. Negative 2 divided by 1/2 is negative 2 times 2. That's negative 4. So I have a point over here at negative 4, negative 3. And then my last point, negative 4 divided by 1/2 is negative 4 times 2. So that's negative 8. I have a point all the way over here at negative 8, positive 3. When I connect those dots together, it's still a very similar shape to what we had. It's just been stretched horizontally. So in green, we have f of 1/2 x. We took the original graph and we stretched it horizontally. So it got pulled out to the sides a bit. And we got that again by dividing by the a value. Regardless of whether it was a stretch or a shrink, we took our x coordinate and divided it by a. So that takes care of all of the stretches and shrinks. We only have one more type of thing to do to our graphs to learn, and those are the reflections. So we'll learn about the reflections, and then we'll put it all together. So let's consider a function y equals f of x. Then the graph of y equals negative f of x is the graph of f of x reflected across the x-axis. So if you're trying to graph a function that is one of our basic functions, it just happens to have a negative on the outside, you take the graph and you flip it over the x-axis. Our other reflection is for the graph of y equals f of negative x. That is the graph of f of x reflected across the y-axis. So for example, if you had your basic function square root of x, and instead you now have the square root of negative x, you would take your graph and flip it over the y-axis. So instead of being over on this right side, it flips over to the left side. Let's do an example. Using a given graph, we're going to look at both of these reflections. So the graph of f of x is given. And we're going to graph y equals negative f of x and y equals f of negative x. So let's give the graph of f of x. My graph of f of x has a point over here at negative 1, 0. It has a point at 2, 3. And it has a point at 4, 1. Here is f of x. So let's take care of y equals negative f of x first. I'm going to graph that one in red. So the negative f of x, remember, that is a reflection across the x-axis. So I'm going to take this graph and imagine folding it over this x-axis, and it's going to appear down at the bottom. Let's start with this point. When I reflected across the x-axis, well, it was already on the x-axis, so reflecting keeps it there. This next point, up at positive 3, when I reflected across the x-axis, it's going to end up down here at negative 3. And this point that was up at positive 1, when I reflected, it's down at negative 1. So here is negative f of x. You just take your graph and imagine folding your paper in half along the x-axis and seeing where it lands on the other side. Now y equals f of negative x, that one's going to be a reflection across the y-axis. So we get to take our graph paper and fold it along the y-axis this time. Points that were on the left side will now be on the right side, and vice versa. So this first point had an x of negative 1. If I reflect it across the y-axis, it's going to end up at positive 1. This point over here had an x of 2. When I reflect it to the other side of the y-axis, that x value is now negative 2. And this last one over here had an x coordinate of 4. When I fold it across the y-axis, it's going to end up over at negative 4. And I get the same type of shape. It just got flipped across the y-axis. So it's like a mirror image if you put the mirror directly on the y-axis. So those are how we do our reflections. Now, all of these things that we've talked about so far in this video, all of our translations, our stretches, our shrinks, and these reflections, they're all called transformations. So these are all transformations of graphs. And sometimes we have lots of different transformations in the same graph. So then we have to figure out what order do I do these in? And the order does in fact matter. Think of it like order of operations when you're calculating a bunch of things. We have an order of operations for our transformations as well. So I'm going to write down the steps for graphing multiple transformations, and then we'll do a couple examples of that. The steps for graphing multiple transformations. Transformations. I'm sorry, I said translations, but it's going to be translations, reflections, stretches, and shrinks. So all of our transformations. We need to use the following order when we have more than one transformation in the problem. First, you need to take care of all of the horizontal translations. So that's all of the shifting to the right or shifting to the left. Do that first. After you've taken care of those, then you do all of your stretches and shrinks. Then you take care of any reflections. And lastly, you do your vertical translations. If you follow this order every time, you'll get to the right final graph. So do all of your shifting left and right, then do all of your stretching or shrinking, then do the flipping across any axes, and then shift up or down last. Let's do an example where we have to do a few different transformations to get the final graph. We are going to graph the function m of x, which is -3 times absolute value, x minus 2, minus 4. So I personally think it helps to write out all of the transformations you need to do and the order that you need to do them in. Then I draw very lightly the graph of the basic function and take it through all of the transformations one at a time. So over here, I will put the graph. One, two, three, four, five, 6, 7, 8. Let's just do 8 everywhere. So your absolute value graph, remember, looks something like this. It looks like a V shape. This was absolute value of x. Now let's take a look at what's going to happen to this absolute value of x when we apply all of our transformations to it. What's the first transformation we have to do? Well, we have to take care of any of our horizontal translations. So shifting to the right or to the left. Do I have any of those? Yes, I do. I have a -2 inside of those absolute values. So my first transformation is to move to the right 2 spots. Then after I do that, I have to do any of my stretches and shrinks. That's this multiplying by 3. That is a vertical stretch by 3. Then I have to take care of any reflections, and that's what that negative is in the front. That negative in the front is going to reflect across the x-axis. And then my last transformation is that -4. That's going to be shifting down 4 spots. So let's do these steps one at a time. First, I'm going to do this first guy right here. Number 1, move to the right 2 spots. So I'm going to move all of my points to the right 2 spots. I'm just going to move a few of my points. If you have a few points that you're tracking, that usually suffices to be enough. So I'm going to be tracking those 5 points that I have there. So we have our V shape still. It's just been moved to the right 2 spots. From there, we're going to do a vertical stretch by a factor of 3. That means I have to take my y coordinates and multiply them by 3. This guy has a y coordinate of 0, so it stays there. These two have a y coordinate of 1, so they get moved up to 3. And my other 2 points that I'm tracking have a y coordinate of 2, so they're going to move all the way up to 6. 4, 5, and 6. So I still have a V shape. It's just a lot skinnier than it used to be. Now I have to do the reflection across the x-axis. The point that's on the x-axis stays there. My other points get flipped down. So this point that was at 1, 3 is now at 1, -3. My point that was at 0, 6 is now at 0, -6. My point that was 3, 3 is now 3, -3. And my point that was over here at 4, 6 is now all the way down at 4, -6. And I still have a V shape. It's just been flipped. Now I have my last one to do, that last transformation going down 4 spots. So I'm going to take each point and move it down 4 spots. Moving this point down 4. This point goes down 1, 2, 3, 4. This point goes down 4. Down 4. And down 4. And that would be my final graph down here. It's a V shape that has been moved to the right 2 spots, stretched by a factor of 3, reflected, and then moved down 4. And I know that's kind of cluttered. I like to do them all on the same graph like that, one at a time, but then I draw my final answer on a separate grid so that it looks a little bit better. So all of this that we did, I'm now going to draw the final graph as my answer. So my final graph, we had a point all the way down here. At 0, -10. Then I have a point over here at 1 and -7. We had our point at 2, -4. 3, -7. And 4, -10. And this is the graph of my m of x. Looks a little bit neater when you don't have all of the transformations on the same graph, but like I said, it helps to show each step. So I like to do that at least on scratch paper, showing each transformation. Otherwise, I tend to get lost doing them all at once. Let's do one more example to finish this video up. Let's graph the function r of x equals the cube root of -x plus 1. So we're going to have to write down our transformations, and we're going to have to look at what happens to our original graph. So remember what the cube root graph looks like at a point at 0, 0, 1, 1, -1, -1, and sort of an S-type shape like that. This was my cube root of x. Now let's see what kind of transformations we have to do. What is the first transformation? Do I have any horizontal shifting? Yes, I do. I have a +1 underneath that square root with my x. That +1 means I'm going to the left 1 spot. After that, do I have any stretches or shrinks? No, I'm not multiplying by a positive number. Then do I have any reflections? Yes, I have a negative in front of my x. That happens to be a reflection across the y-axis. And then lastly, do I have any vertical shifts? No, I don't. I don't have any adding or subtracting going on outside of the square root. So this is only 2 transformations that we have to do. First transformation, go to the left 1 spot. So I'm going to do that in green. I'm going to take my 3 points that I have and move them all to the left 1 spot. Now I get to do my other transformation, reflect across the y-axis. So this point that's on the y-axis is going to stay there. And then the points that were on the left side are now over on the right side. And this guy as well was on the left side at -2, and it's going to reflect across to be over at +2. And we get that shape over there. Now this one's not as cluttered as the last one that we did, but I would still draw the graph separately just to emphasize what my final answer is. So let me quickly draw my final answer of r of x. So my final graph of r of x has a point here at 1, 0, a point at 0, 1, and a point at 2, -1, and then it still has the general S-type shape of our cube root. Here is r of x for our final answer. And that's all I have for you today. Graphing can be pretty complicated. It helps if you have some nice graph paper, as I'm sure you can tell by watching on the whiteboard. And it also helps to sometimes check your answer with your graphing calculator. And again, if transformations really aren't your thing, remember that you can always make a table of points and plot them that way. But I do think it's much quicker to use the transformations when you can. So it helps to know your basic functions so that you can just pick up those graphs, flip them around, stretch them, add things to them, reflect them, all of that. Much easier that way. If you have any questions, feel free to drop them below, or if you're a current student, you can email or ask in office hours, and I will see you for the next video.